If I have a long line of charge, okay, so think of this. This is a whole line of charge. So in the point charge, we have to choose a Gaussian surface that has the electric flux density to be constant all around that Gaussian surface. So for line of charge, can you think of what the Gaussian surface, what is the best Gaussian surface to choose so that you have a constant electric flux density or electric field around that surface? You can't choose a sphere because you have a line charge. If you choose a sphere, then it will not be constant. Okay, so you have to choose something else that gives you a good or simple integration. So we want the electric flux density to be constant on the surface, and then we want the vector to be in parallel. We want d and ds to be in parallel so that the dot product is also simple to solve. Okay. So the best is a cylinder that has closed on both ends. So my example of earlier one will be my backbend tin. Okay. So in this case here, if I choose a cylindrical Gaussian surface that has my line charge running through, and we know that the electric field going to point radially outward from the line charge. So the top and bottom of the enclosed surface, okay, so think of this, my backbend tin, I have my line of charge going through. So on the top surface and the bottom surface, there will be no electric field because remember just now when we talked about the surface vector, not the electric flux. So it's not cutting through the top and the bottom surface, because if I have my line of charge here, then the electric flux density is going to point radially outwards. Okay, so it's going to point outwards. So on the top surface, it'll be doing this, and therefore it doesn't cut through the top and the bottom surface. Okay, so the electric flux on the top and the bottom will be 0. The electric flux is only on the curvature of my cylinder. Okay, so top and bottom, the flux is not trading through. We call it trading through the surface, but it's only trade through the curved surface of our cylinder. And then we define line of charge as a charge density, and the charge density of a line of charge is called lambda, and that will be coulombs per meter. So the total charge will be over a length. So the charge density times a specific length that gives you the amount of charge of that length. Okay, so we can now apply our Gauss law to this scenario. Okay, so the electric flux density, closed surface integral d dot ds, and we know that in this example, so again, our surface vector ds is in parallel to our electric flux density. So our dot product is just the magnitude of, or multiplication of the magnitude of the two. And then d is also constant all throughout this curvature surface. Okay, so at every point, d is constant because they are of equal distance from the line charge. Okay, so that are the two ingredients you need to choose your Gaussian surface. You want it to be constant on the surface, and then you want them to be in parallel, and that fulfills both of them. Okay, so d dot ds can be simplified to d times ds of the magnitude, and d is constant. We can take d out of our integral, And then this is simply the curvature area of our cylinder, which is 2 pi r times L. Okay, so our cylinder, so this distance, this area here, which is 2 pi r times L, that gives me the curvature area, and therefore that has to be equals to Q, and Q is equals to lambda times L. Okay, so this is in coulombs per meter, this is in meter, and that gives us our charge that enclosed inside this line of charge. Okay, and therefore we work out that the electric flux density of a line of charge is equals to lambda over 2 pi r. And we obtain the same result for D whether or not the line of charge sits in free space or in dielectrics, because the charge D only depends on free charge again. And then we can find the electric field by equating D equals to epsilon r epsilon naught times E, and we work out that the electric field is equals to lambda over 2 pi epsilon r epsilon naught times r. Okay, so this is for a line of charge. And you can see that the line of charge is proportional to 1 over r, unlike for point charge, it's proportional to 1 over r squared. Again, you can convert that back into vector by multiplying by the unit vector of a radial unit vector. Okay, so that is line charge.